Bien, bueno, vamos a comenzar. A ver, ahí vienen más personas. Bueno, pues buenos días a todos. Gracias por su presencia aquí en el seminario. El día de hoy tenemos al doctor Chunyan Lee, es oceanógrafo físico de la Universidad Estatal de Luisiana. Esto nos queda así arribita donde estamos nosotros, ahí están localizados ellos. El doctor Chunyan es oceanógrafo físico por parte de la Universidad de China. Allá estudió su licenciatura y su maestría. Tiene un doctorado en la Universidad de Connecticut en oceanografía física. Y él se ha especializado mucho en investigación en la interacción océano-atmósfera, de cómo los fenómenos meteorológicos, como los nortes, los huracanes, cómo estos forzamientos afectan principalmente a la circulación de lagunas costeras y los intercambios que puedan haber con el mar adyacente, ¿no? El doctor Chunyan es un excelente oceanógrafo, trabaja modelación numérica. Ellos tienen un modelo numérico que desarrollan muy particular, creo que se llama FBCOM, que es como de alta resolución, y también tiene mucha experiencia en datos in situ, donde toman datos con arrastres de ADCP parecidos a los que hacemos nosotros aquí, y también con equipos de estaciones meteorológicas y equipos anclados en el mar, y hacen una serie de análisis físicos que complementan sus modelos numéricos para tratar de establecer el entendimiento de los intercambios de volúmenes de agua entre este tipo de cuerpos muy costeros con el mar adyacente, y pues llevarlo a diferentes objetivos de manera particular. El día de hoy nos va a presentar el trabajo que se llama Impact of Moving Weather Systems on the Coastal Ocean Circulation, justamente eso, ¿no? El impacto de sistemas atmosféricos en la circulación oceánica de cuerpos costeros. Y Chunyam, I'm sorry I did the introduction in Spanish. So, con ustedes el doctor Chunyana. Can you hear us?
Yes, thank you for the introduction. Can I start?
Yes, please.
Okay, let me share the screen first. Buenos días a todos. Thank you, Alex, for your invitation. And thank you, everyone, for coming and allow me to share some of my work with you guys, with your colleagues here at the CESAL, Yucatan, Mexico. My name is Chunyan Lee, and today I'll be talking about the impact of moving weather system on the coastal ocean circulation. The coastal oceans are constantly responding to the atmosphere above them, and like hurricanes, tropical storms, cold fronts, they all pass over the oceans, and each with a pattern of wind. And these moving systems impact the coastal currents and the exchanges with estuaries and the shelf, the continental shelf. Examples from our own observations showing how the ocean reacts as these systems move through. I will then discuss briefly on a Laplace transform model to describe how the velocity field responds to time-varying forcing. And due to time constraints, because we only have like half an hour, my presentation will be brief, and I will welcome questions and comments and discussion afterwards. Okay, the moving system, weather systems, and major questions we're dealing with. By moving weather system, I meant the synoptic weather systems, like the high pressure system, low pressure system, extratropical cyclones, And those associated with those extratropical cyclones are the cold fronts, warm fronts, stationary fronts, um, and also including hurricanes, tropical storms. Our main question is how will these moving systems affect coastal ocean and the estuaries? And you can see this somehow the animation looks like stopped. Can you guys see the animation moving?
It stopped. It was moving, but it stopped.
Yeah, okay. It's supposed to be keep looping. But anyway, look at the scale. Um, the scale is thousands of kilometers. And those blue lines with triangles, blue triangles, they're cold fronts. And those red lines with semicircles, they're the warm fronts. And the alternating blue and red, they are the stationary fronts. And those are large scale features and they vary all the time. Okay, let me see. Looks like, is it advancing? Okay, good. So the main objective of the study is uh, to determine the impact of coastal currents, impact of the weather systems to coastal currents, and impact of the coastal currents like the fronts, which are associated with extratropical cyclones, and the tropical cyclones to the exchange flows in the bays or flushing of the bays, and also to look at the impact of the weather systems to the multiple inlet estuaries, which are abundant along the northern Gulf of Mexico coast. Here is a selected references based on which I'm going to discuss today briefly. I cannot talk all of them, but just pick out a few examples, three examples. We are focusing on the exchange flows and their modes in multiple inlet systems and the coastal currents and the tropical storm interaction with cold front. And I will specifically discuss, although briefly, Laplace transform model and the ideas behind it. Okay, first I would like to review with you guys of what is an extratropical cyclone and the fronts associated with it. This is a map showing a typical extratropical cyclone, which has a low pressure center indicated by L, the letter L. It's the center, which is the minimum air pressure. And then you see the blue line, which is the cold front. And associated with this extratropical cyclone is the cold front, warm front, and the warm advection and cold advection. So warm advection is the current coming from the Gulf of Mexico, which is warm and damp, so with high humidity. And after the passage of the cold front, the wind switches, the pressure will increase. So at the passage, the pressure, air pressure reaches its minimum. Okay. And then the dry air and cold air will come in through. All right. So it's a switch of the wind as well. And that's the cold advection. So that variation of wind is associated with the movement of the system. And the movement, the trajectory of the system basically is moving from the west to the east, or north to south, and sometimes loop back. So it's kind of dipping to the south, then moving to the north. Um, Sometimes along the east coast of the US, forming a severe weather system, maybe having some flooding effect, what we call northeasters. All right. So this is a typical example of kind of uh, wind vector time series. Okay, with cold front passage, kind of repeated cold front passage or sometimes with sea breeze, land breeze. But a typical cold front wind is such that it has what we call prefrontal wind, which is kind of southerly wind, and varies with direction. And then after the cold front passage, which is indicated by the red line, that's when the front pass. The wind will switch abruptly to a northerly wind. As this unfolds, the wind usually rotates kind of clockwise in northern hemisphere. All right, it may vary, depends on situation, but typically it rotates clockwise and similar in the fashion similar to an inertial oscillation. Okay, our study method includes using bottom-mounted acoustic Doppler current profiler and also side-looking acoustic Doppler current profiler on the coastal structure. And we also use vessel-based observations with vessels equipped with downward-looking ADCP. We also use numerical models to do experiments and combine with time series analysis, statistical analysis, like empirical orthogonal function analysis or principal component analysis. And then, of course, we use theoretical analysis. Today, I will present briefly a Laplace transform model and results and what it means. First, the traditional idea of coastal circulation in the northern Gulf of Mexico is such that it's mainly is seasonal. Okay, along specifically along the Louisiana, Texas coast. There is a coastal current, sometimes called a coastal jet. It's a seasonal feature, so it mainly flows down coast, meaning from east to west. Basically has two reasons. One is the Mississippi River flowing out, and then we have the southeasterly wind kind of pushing water to the west, and also the impact of Coriolis force. The Earth's rotational effect tend to make the current hugging the coast and moving in the direction of Kelvin wave. Okay, so the current is believed to be part of a limb of a gyre which has a return flow at the shelf break. Okay, so you have the flow going to the west and then coming back in deeper water, forming a loop. Okay, that kind of current is seasonal and varies with time, of course, but it reverses in the summertime. So that was a traditional picture of the along the Louisiana, Texas coast. Okay, so here what we, for the first example, what we were aiming at is looking at the coastal current and looking at its variability and its response to the weather system. And we were lucky that while we were out there, we were right after the passage of a cold front. And it turns out to be a relatively strong cold front in the month. Okay, so within like 30 days, we had several cold front passage, but this was the strongest. We were running along a transect across the shelf from A to B to C. So A, B, C are three stations that we stop with CTD cats. Well, we had water samples, collected nutrients, CDOM, and at the same time measure the flow current. The flow current is measured continuously and recorded on a 2-minute average time series. Okay, so the time was March the 3rd to the 5th, within 36 hours in 2021. Okay, during COVID period. The sampling was quite successful. We repeatedly sample this transect 12 times within the 36 hours. So we had 36 replications of the flow structure, as you can see on the right-hand side, the 12 snapshots of the flow. Shown here, the vectors are the horizontal velocities. So if the velocity vector is upward, that means it's to the west. If it's downward, it's to the east. If it's to the right, meaning it's to the north. If it's to the left, that means it's to the south. Okay, so we kind of put the two-dimensional horizontal velocity onto this map. It varies, of course, it varies, and the wind vector is shown as the red arrow. So you can see during this time, the average wind is which direction. That's like this is northerly wind. Right after the passage of the cold front is a northerly wind. Then the northern wind is reduced. Okay, then it rotates to the east wind and becomes a westerly wind, then northerly wind again. So it varies. Okay. This shows the weather map. That's when the survey kind of started. This is the cold front just passed a few hours after we started. That's the cold front. And after the cold front, you see it's mainly occupied by a high pressure. Okay, it's very typical for a cold front passage. After passage of the front, it's usually a high pressure system, which is dry and cold. Okay, and on the right-hand side, you can see the wind speed. So wind speed in the beginning, before the survey, okay, the survey was in a period highlighted by this gray area. The red lines are the beginning and the end of our survey. So before our survey, the wind was strong because the cold front just passed, and then it decreased as we started. The wind was still decreasing and bounced back and decreased, but the overall trend is decreasing. The wind direction varied, of course, and air pressure was increasing as the cold front passed, which is very typical because of the high pressure system occupy the region. So you can see the high pressure is occupying the area during our survey. And the wind pattern, it varies, but mostly from the north, okay, northeast wind. That's a diagram showing the high pressure system and the coastlines here. And because of the high pressure system, our wind in the sampling site is mostly from the northeast. Okay. And the scale, I want to emphasize the scale is pretty large, that the cold front is on the order of 3,000 or 4,000 kilometers in length. So it's a very large scale feature. Okay. So here's our transect from A to B to C, and then we projected the transect onto the north, south, and east, west transect, and then we can integrate the velocity across the vertical transect to get the volume transport in the east direction and also in the north direction. So this is the east direction. We call it along shelf transport, and then the cross shelf transport. These lines, the dashed lines is the positive component, and the red line, the solid line, is the total, and the negative part is the dashed blue line. So 0 is here. So that means the transport is mostly to the west. Okay, along shelf transport is to the west. Very little to the east, maybe near the bottom or on the side, you have a little bit return flow, but mostly it's all driven by the coastal, by the wind. It's along the coastal current direction to the west, from east to the west. That's along shelf component. But the cross shelf component, you can see oscillations. Okay, that oscillation is kind of similar to the um, tidal oscillation, and it has two-layered feature. So you have a negative component, positive component. One is above zero, one is below zero. Okay, that's the net. The solid line is the net. The blue line, dashed blue line, is the negative component, which is the surface. Okay, the surface current is flowing to the south, so it's a negative, and the bottom is flowing to the north. So it's like a two-layered flow, very much like estuarine circulation, because the coastal current is lighter, it's fresher, warmer, so it's flowing on the top and out. But keep in mind that the majority of the flow is still along the shelf because the um, transport along the shelf is bigger. Okay, it's 12 times bigger, so it's one order of magnitude bigger than the cross shelf transport. That's one thing. The other point is that pay attention to the along shelf transport. That magnitude started with much bigger, then decrease, bounce a little bit back, and then decrease continuously. The change is by 3 times. So over the 36-hour period, the transport reduced by 3 times. Okay, not to mention that uh, in the beginning, the wind was even stronger, so which we didn't capture. Well, so it must have a greater along shelf transport that we didn't capture because we started a little late after the passage of the cold front. But still, we can see the transport reduced by 3 times. And that's a contrast to the traditional view that the shelf circulation is kind of seasonal. But we captured the 36-hour very short time period, significant variation. On the other hand, the cross-shelf transport barely responded. It's basically keep oscillating as a two-layered flow and did not have a very significant indication of the effect of the wind. That was a very short time sampling, of course, even though it's very intense. But we also have a long-term observations, but during a different time, different season. We had multiple samples, many data sets from different years. In this paper, we just picked the 2017 summertime period, for about 40 days, 40, 50 days of sampling period, which happen to have captured two cold front in the summer, which are usually very weak. Okay, so the cold front is usually very strong in wintertime, in the cool season, in the early spring and wintertime, and late fall, of course, between October and the next year's April. But this is during summertime, all right, 2017, and we captured two weak cold fronts and two hurricanes. One is Hurricane Harvey, which was very severe, caused a lot of compound flooding in Houston area. Another one is also severe, caused a lot of damage in Florida. So one is on the west, one is on the east of our sampling site. And the deployment was pretty much right on the sampling transect. Like this is the transect. Our mooring was at the shown by the cyan, light blue, and the blue color. So that's the two stations. We have two ADCPs sampling at the same time. So here I'm only showing one ADCP results. on the right-hand side is the raw data for U component and V component. On the on the left-hand side. On the right-hand side is a low-pass filter results, and you can see the impact of cold front here, and Harvey and Irma, because Harvey is on the west, Irma is on the east, and they are from different directions, and their wind therefore is different, and their wind is producing exactly the opposite flow feature for both U and the V. You can see Harvey has a red color, right, and the blue color for Irma. So they're kind of opposite, and that indicates that the position of the hurricane also matters. And on the left-hand side, you can see the oscillation. And many people may think that the oscillations are tidal oscillation. It's in fact a mixture of kind of weak tide and the inertial oscillation. So they are kind of all mixed together because our sampling site is at roughly 30-degree latitude, which is an area where the inertial oscillation frequency is almost the same as a diurnal time. So they all have roughly 24-hour period. So that will give us a resonance. That resonance will make the wind-driven inertial oscillation appear like a tidal, a diurnal tide. So they superimpose onto each other, make the diurnal signal stronger, but it's kind of relatively random, not as regular as the strong tide. Okay, so this is a rotary spectrum. Not sure if everybody is familiar with rotary spectrum. Basically, the Fourier transport gives you a spectrum, which is a superposition of sinusoidal motions at different frequencies, right? And if you use a exponential format to express the Fourier transform, you have a negative frequency and positive frequency. But for real functions, they're the same. They have same magnitude for negative and positive. So usually we just folded them together and multiply by 2, get the energy that way. But since we have U and a V, it's a vector, and the vector is going to have rotation in either clockwise or counterclockwise directions. Okay, so basically, long story short, for any vector like U and a V, velocity, horizontal velocity, the Fourier transform can be for any time series. It doesn't have to be purely tidal sinusoidal. So any continuous function for U and a V, you can consider it consists of 2 components. One is rotating clockwise, which is the same direction of inertial oscillation, and the other one is opposite direction, superimposed onto each other. And the relative magnitude will give you the total variation. Okay, so this is the rotary spectrum giving you the 2 spectrum for 2 different directions. The blue line is the clockwise spectrum. The red line is counterclockwise spectrum. So we call it rotary spectrum. That gives you an idea whether it's you have inertial oscillation or not, right? Like here at the inertial frequency, which is roughly 1 cycle per day, we have a peak, okay? And the other rotation, the counter-inertial direction rotation is very weak. So that indicates that most likely this is inertial oscillation. But in fact, of course, we do have tide. So it's kind of a mixture of kind of weak tide and inertial oscillation in responding to wind. Okay. And also the signal strength decreases with depth, right? But it all shows the same feature. That is, the inertial oscillation energy is bigger than the other rotation. Until you reach the bottom, then you don't see. It's at the noise level. Okay, so basically the moving weather system, the diagram shows the prefrontal and postfrontal. So the prefrontal wind and postfrontal wind, the wind changed because the moving weather system, as it moves, the wind will evolve, right? And of course, in between, you have a variation between the passage and between the prefrontal and postfrontal, you have a variation. It's a continuous variation. And for the hurricane case, if the hurricane is on the west side, on the east side of the sampling site, you have different wind direction. One is experiencing northerly wind, one is experiencing southerly wind. So that will give you a kind of opposite forcing in terms of the direction as a vector, right? So the moving system uh, makes a difference in terms of what the wind is giving to the coastal ocean. Okay, the coastal ocean is experiencing different forcing as the weather system moves. Okay, the second example is when a cold front meets a tropical storm. So this is our sampling site at the Atchafalaya Bay, and we had ADCP there, 2000. I think we deployed from 2008 to 2009 and lasted until 2012, something like that. And during 2011, while the deployment was still active, there was a Tropical Storm Lee, which was kind of uh, history making. Usually, tropical storm is very weak, right? Relatively speaking, compared to hurricane. But this time, the tropical storm comes in, make landfall right at our study site, and then immediately merge with a cold front. So the two systems merge together, force a stronger system that produced kind of history-making precipitation along the track all the way to New Jersey. So it's a severe weather system that we were lucky enough to capture it while our ADCP was measuring the data. Okay, the velocity reached 2.5 meter per second at its peak. All right, so what we're trying to do is we try to look at the response of the ocean currents right at the inlet. This inlet is a kind of narrow inlet, but very, very deep, 35, at least 35 meters, at some point close to 40 meters. For a bay that is very shallow, it's like 1 meter, 2 meter average depth. So very shallow bay, but the scouring of the strong tidal current make a very deep channel, 35, at least 35 meters. All right, so we had an ADCP there. What we did was we had an unmanned boat. We computed the transport, cross-channel transport with a 24-hour survey, continuous survey. So we kind of linearly related between the transport and the current, the mean current velocity from horizontal ADCP. Then we establish a regression, and then we can back calculate the entire period of the transport, including the time when the tropical storm passed the region. So we can compute the transport during that time period, and then we analyze that. Okay, so that's the weather map showing you the after the landfall of the tropical storm, and you see the cold front is approaching, and they merge together, and that formed a extratropical cyclone afterwards. And this extratropical cyclone then moved to the north, passing multiple states, then before it goes to the ocean. Okay, dumped a lot of precipitation along its way. Okay, so you can see the wind, the land measured wind, and this is from our station offshore. We had a offshore station on the oil platform that shows the evolution of the wind. The southerly wind then switch to kind of northwest wind, westerly wind, and it rotates. And after the cold front passed, we had a significant northerly wind. All right. So the air pressure was the deepest, the smallest when the tropical storm passed region. Then it goes back, and when it merged with cold front, it fluctuated a little bit, then keep going up when the high pressure system arrived. Okay, the velocity, you can see that the velocity at its peak close to 2.5 meter per second. And the lines show the timing of the landfall of the tropical storm and also the passage of the cold front. So they combined force make the strong cross all along the channel velocity. So this is along channel velocity. Okay, the cross channel velocity is the blue line, very small. So majority flow is go along the channel. Okay, so this is the track of unmanned boat, and this is the profile of the water depths, showing you along this transect, the deepest water is like 30 meter. All right, I'm using that transport measured at one day, sometime in 2009, 2010 actually. That's 2010. We had the transport from the unmanned boat measured using ADCP, and the mean velocity from the horizontal ADCP, and they have a very good regression. Then we can compute the total transport. So this is the time series of the transport we pick out for the time period of the event. Okay, you see the event, you have a peak here, maximum, and of course it's on top of the tidal cycle. So if you apply a low pass filter, it will give you this lower value, but still you can see the peak during the event. Okay, so this shows the snapshots of the wind evolution during the time. So that's before the tropical storm formed. You can see mainly it's easterly wind. Then the tropical storm started to form and started to increase. And I mark the red arrow of the wind kind of at our sampling site, which is somewhere here at this point. Okay, so the wind evolves, and notice it rotates. It rotates kind of in this cyclonic fashion, because we have a cyclone here. Cyclonic fashion rotating before the cold front passed, then we have a push from the north, from the northeast. Okay, so the post-frontal wind is a strong northerly push. That corresponding to the flow mode that has the first mode and second mode. The first mode is a kind of through flow because the rotating wind produce a vorticity that drives the wind through the opening here, the wide opening, and coming out of this narrow southeast pass. All right, so that's because of the combined vorticity from the tropical storm and cold front. They all have the same vorticity, kind of cyclonic vorticity. Okay, then post-frontal wind is from the north, push everything out. So that also intensified the strong outward flow through the inlet that we recorded. Okay. The third example, very quickly, I will just briefly introduce this. This is a little bit earlier work, published 2019. What we did was we looked at 51 storms associated with cold front. And we had multiple ADCPs out there measuring the flow, and we used that flow data to validate numerical model. Then we simulated all the storm events and the impact to the flushing of the bay. Basically, it's Barraterra Bay. Okay, so it's a very shallow bay with multiple inlet. We have 4 major inlet. We have probably 3 on the East Coast, 3 more very shallow, but with very little communication. So we only focus on the major inlet, the 1, 2, 3, 4 inlets. All right. On the right-hand side, it just shows some example of the 51 storms that shows the cold front passage. So the vertical lines are the timing of the cold front passage, and the lower panels are the upper panels are the measured velocities. Okay, the time period was somewhere between 2013 and 2015. Several cold front seasons. We had 51 events recorded. Okay, here is the result. It's kind of busy. I apologize for the complicated graphs, but I will just briefly discuss that. Basically, here on the top in the center is the volume transport computed from the numerical model for the 4 inlets. Okay, and the vertical lines are the timings of the cold front passages. You can see it goes up and down. It's all low pass filter, so we filter out the tidal flushing. Okay, so it's kind of hard to see the impact, and therefore we resorted to we try to use EUF analysis to try to pick up the patterns. Okay, it's kind of complicated, but we can summarize it into 3 major modes. The first mode is kind of all in, all out. So when the front, the pre-front and cold front wind comes, you have increasing wind. You will push everything into the system or pushing it out during the post-front phase. All right, so during that phase, you're going to have everything going into the bay, or reversely, everything comes out of the bay. That's first mode. Okay, occupy about 45% of the simulation time for the 51 storms. And the second mode is that the major inlet, they have the flows kind of against the wind. The shallow inlet, they have the flow with the wind. Okay, so that occupied 41%, and that occurs. We see that from different systems. Earlier paper for other systems in the East Coast show same thing. You have basically the wind push water so that the shallow water inlet will go with the wind. And then in deeper water, you have the counter wind flow. Okay. And also during the relaxation period, that when the wind is reducing, the flow try to kind of, rush out through the major inlet. Okay, so this represents second mode. The third mode is a little complicated to explain, but it has less percentages, 13%. It's similar to like if you have an inlet, like upstream inlet, a downstream inlet of the wind. So you have wind from upstream will push things into the bay, and then downstream you will push it out. So things like that will produce that kind of mechanism will produce this third kind of mode. All right, we also look at all the 51 storms, look at the intensity. So we defined a cold front strength index based on the wind magnitude and also the air pressure drop. So using the two parameters, normalize it so that they are all non-dimensional and add them together, get index. We call it cold front strength index. It showed that as the index increases, yes, indeed, the velocity anomaly will also increase. That's the response of the exchange flow in the multiple inlet system to cold front passages. So these are my three examples. All right, so our problem, we can state it in the mathematical resolution. We're looking at the wind vary with time, right? And oftentimes when we study the subtidal exchange flow or the tidal flows is sinusoidal, relatively easy. And then subtidal flow is kind of mean condition, is kind of relatively constant. These problems are relatively easier to solve in mathematics. But if we would like to look at the evolution of the wind-driven response in the coastal ocean, everything changes with time. All right, so it's a time function, and that presents a challenge. Okay, as the weather system moves, the wind will change with time. Okay, so it's a kind of initial value problem. So it's given an initial velocity field and the variable wind field, which change with time. How will the coastal ocean respond accordingly, right? So that's a kind of initial value problem mathematically. We stated it in this way for this mathematical problem. Most theoretical models, they either deal with steady state problem or kind of periodic problem, like a tidal situation, or subtidal situation is a steady state problem. But in this case, it's a little bit different that we are looking at the initial value problem after which everything evolves. How will the evolution go, right? So that's the question. And one mathematical tool that we can use is what we call Laplace transform. So what Laplace transform is, it is a mathematical operation that that you do it with a given initial value problem. So initially you have a condition. We're not requiring it to be zero. It could be zero, but we're requiring to have some initial condition. And then we have the forcing changing with time, and we do a Laplace transform. Okay, so Laplace transform is at the bottom of the left side. Okay, so this is a Laplace transform. Here, P is a complex parameter, and psi is the function. So here is our function, is our velocity, is our elevation, or our density, or wind stress, any of the variables. Okay, so we use a two-dimensional shallow water equation. Okay, so it's a shallow water equation with Coriolis force or Coriolis acceleration on the left-hand side. Then you have a pressure gradient for barotropic. You have the air pressure effect. You have the density-driven, density-induced baroclinic pressure gradient force. And then you have the wind stress force and the bottom stress force. Okay. And here we just expand it into X and Y directions and linearize the bottom friction. So the first order bottom friction, the bottom friction is quadratic to start with, which is nonlinear. We can expand it. So we have a linear part. We keep the nonlinear part and lump into the advection part. So the NX and NY is all the nonlinear terms, the advection plus the advective, well, at the nonlinear part of the bottom friction. So we lump into the n term, okay? So then we apply the Laplace transform, and then we do Laplace transform, we rearrange the equation, we solve the transform the velocity. Okay, then we do a inverse Laplace transform. After we do the inverse Laplace transform, we can express it in this way. I omit all the mathematics, but this is the result. Okay, so you have a u and the v component with different contributions from initial value. So these are the initial value contribution. And then you have the nonlinear contribution. You have the pressure gradient contribution, density gradient contribution, and wind stress contribution. Here, the F1 and F2, they are functions that's related to two things. One is the Earth's rotation, and second is bottom friction. So the Earth's rotation is giving you kind of inertial oscillation. That's the cosine ft. F is the Coriolis parameter, which is 2 omega times sine phi. And omega is the angular velocity of the Earth, which is equal to 7.29 times 10 to minus 5 per second. Okay, and sine phi is the latitude. All right, in our study site, it's roughly sine 30 degree, which is 0.5. Okay, and time, t is time. Beta is the friction coefficient. Okay, so this is kind of complicated. If I write it out, it will be a full page. But I simplified it. One way to simplify it is that we combine U and V together to a vector format, but we are not using the general vector format. Instead, we're using complex format. We use U plus IV. So this is a complex variable, which is basically a vector, right? U and V give you the direction and the magnitude of the velocity. And turns out this is a beautiful expression that it shows that you can lump everything together into a very nice expression that all the forcings, like the initial condition, the nonlinear flow contribution, and the pressure gradient force, the density-driven component, and the wind-driven component, they all can be expressed by a collection of convolutions. So convolution is this big circle with a cross. So this is a definition of convolution. If you learned before, this is a quick review. You have two functions, cosine and phi, and you put them together, do a mathematical transform, which is integration with this. Okay, so this is called a convolution. Convolution is a apparently abstract mathematical operation, but it has useful applications. For one thing, nowadays very hot is the AI, right? The artificial intelligence, machine learning, and has a lot to do with convolution. So a lot of the mathematics come from the convolution. And secondly, in conventional science, the signal processing theory, that convolution is also kind of filter. Okay, so it can filter out like low pass, high pass, band stop. And those filters can be achieved by convolutions. Okay, so here we have a convolution where all the forcings, each forcing is convolving with a function which I called this complex frictional rotary inertial function. Okay, it's a mouthful name. Okay, so it's a CFRIF, which is basically inertial oscillation function with frictional decay. Okay, so this is inertial oscillation function, and this is frictional decay, exponentially decreasing with time, right? So that's the function convolving with all the forcings. So that result I call the convolution theorem. which is very nice because it's so simple conceptually, right? So with all these complicated terms, I just pick out one of them, just the wind. Okay, so the wind stress term, I pick it out, and using the wind, I call it rotary wind stress, which is in complex format of the wind stress term. You have the x and y component expressed in one complex variable. And imagine we do a Fourier transform. So we have two components. One is rotating clockwise, one is rotating counterclockwise. So the clockwise rotation, which is this term, is the inertial oscillation kind of oscillation. Okay, this one, the A omega is the other way, is a counter inertial. Okay, so then we use this forcing, which is here, forcing is G, right? F is this, is for every term is the same for this frictional inertial oscillation frequency function. But for the forcing, it's different for each term. And we are only looking at the forcing from the wind stress, which is this forcing. And if you substitute into the expression, just look at one component of the Fourier transform. So meaning we just look at one frequency, omega. Okay, we can add all the omega together, get the total expression, but just look at one omega for simplicity. So that will give us this result for counterclockwise rotating component and clockwise. The clockwise is the inertial oscillation component. Okay, so these are the result. Seemingly complicated, but if you look at the magnitude, so the A and the B, they're representing the magnitude of the wind, so wind forcing. Now, if we just look at the amplitude here, okay, the amplitude of this whole thing except the wind part, the amplitude of this function, kind of intrinsic gain, okay, it's the gain or the magnitude, whether you amplify A effect of A or amplify effect of B or reduce the effect of A or B. Component and clockwise component. All right, you can verify that the counterclockwise component has a magnitude that's smaller than the clockwise component. Okay, so this is the inertial oscillation component. This is a counter inertial oscillation component, and that result says the inertial oscillation component is bigger than the other component. And that's also explainable by the filtering effect. So this is a filter. The convolution is a filter. It filters out inertial oscillation component. And that's why we see coastal ocean and deep ocean, when the storm passed by, we have inertial oscillation, we have only one rotation retained, and the other direction is not as strong, okay? And that's shown by the result here, like I showed you earlier, that the inertial component is bigger than the counter inertial component, verified by the theory. Okay, we see that all the time, from different site, from different time period, different locations, they're all the same. Okay, so the Laplace transform model result in a quick summary is that the convolution is a convolution theorem, that the velocity response to forcing can be expressed nicely as a convolutions added together with the complex frictional rotary inertial function that I showed. And this framework clarifies the mechanism of tide inertial resonance and wind inertial resonance because this term as F and omega, when they are the same, this becomes 0, right? So this becomes maximized. All right, while this is big, when you have F equals omega, omega and F is the same, you have 2F, right? So this is a big number, so this is small. When this is approaches 0, this reaches maximum. So the maximum will give you a resonance, a tidal resonance with tidal frequency, or the wind resonance when the wind frequency is similar to the inertial frequency. They have a strong oscillation. Okay, both mechanisms are active in our region because at 30° north, the near equivalence between the diurnal tidal frequency and the local inertial frequency, they will enhance the resonance, amplifying the relatively small diurnal tide otherwise. Okay, so I will produce tide-like, but kind of irregular velocity variability in the region. Okay, this kind of resonance explains the observed dominance of the clockwise near inertial oscillation. Okay. So in summary, the contributions to form various forcing functions are through the mathematical convolution between forcing and the complex frictional rotary inertial function. Okay, and the integrated effect of the history of the forcing is important because it's a convolution, it's an integration. So wind history is also relevant. And the function, the CFRIF function is effectively a frictional rotary filter that favors the inertial oscillation because it filters out inertial oscillation. And the repeated extratropical cyclones, because they happen all the time, and the associated frontal passage, they dominate the flushing of the multiple inlet estuarine systems, as we demonstrated with the 51 storm examples. And the impact of the tropical cyclones varies with the path and the trajectories. The coastal current and the transport, they're significantly affected by the coastal frontal passages. Okay, with that, thank you everybody for your attention. Welcome any questions.
Thank you, Chunyan. Can you listen to me?
Yes, I can hear.
Okay. Now we're gonna have some time for questions. Nada, todo lo entendieron. Eh, Chunyan, I have a question.
Okay, go ahead.
Well, you show us three different experiments, more or less showing the interaction of different atmospheric forcings, but how these affect coastal bodies of water, right? So which were your main objectives besides all these super nice mathematical introduction that you give us? Like you were looking like for exchange of not, like nutrients inside inlets or larvae. Can you talk a little about those impacts or implications?
Yes, yes, that's a very good question. Yeah, since I presented three different examples, and they actually had originally had kind of different objectives, right? Our focus is slightly different. Like for the multiple inlet system case, I was focusing on the exchange between the estuary and the shelf, right? For the coastal current case, I was looking at mainly the coastal current variation. And also, like I mentioned, that we did some collected some water samples for nutrient. So the main idea was actually to look at the the collect non-aliased transport of materials. So what people usually do for water samples, they get, carbons, they get nutrient flux. They just sample, like go there this month, go there, next month, go there. Or maybe today just collect one sample, and next day collect another sample. And in signal processing, that kind of sampling, we say it's alias sampling, meaning you're not really resolving the tidal oscillation because the tidal oscillation makes things very variable over a tidal period, right? If you just pick one sample, it's not really reliable. So the idea is to sample repeatedly during one tidal cycle. We repeat many times, so we don't have a alias sample. Rather, we have a more reliable sample capturing both flood and air at different tidal phases. And that's what we did for the coastal current example, that we collected water samples, we computed the flux, the transport of carbon and different nutrient species, which we had a separate paper by a graduate student, which was just accepted today. So that was what I didn't present, because that's from our same survey. Okay, the same survey, we collected physical data, biological data, the chemical data. The goal was really a lot bigger than just the physics, but physics is the driving force, is the background. It's the variation of tidal variation, inertial oscillation variation, and also the wind-driven variation that drives the variability that have a strong implication to the carbon flux to material transport in the ocean. I hope I answered your question.
Yes, yes. Thank you very much. I think we have somebody in the Braulio.
Yep. Can you
Hi,
hear me?
brother.
Yes, I
Yeah.
hear.
Hello, Professor Lee. How are you doing? Very nice talk. I'm intrigued about the effect of the wind from the cold fronts on the density gradients, because you explained that you have this Louisiana current interacting in the system. So how the cold fronts affect this transport of the Louisiana current, and the density gradients affect the airspring flow. And if this is introduced in the Laplace, like you the last model, the last theorem that you mentioned, because you have the density gradients, right? Introduce that. Can you extract that information from density gradients?
Yes, that's an excellent question. And let me see if I have that diagram, but let me see if I have that somewhere there. But we did present in the paper that if I have it, that'd be great. If I don't, I will just explain to you. Okay, looks like it's not here, but that's an excellent question, because our model really did show the effect of the density gradient, right? And the density does have a measurable significant gradient, because, like I mentioned, that there's a kind of estuarine situation. You have fresh water from the ocean, from the coast, and the coastal ocean offshore was having higher salinity. And we computed the density contribution, which showed that the density contribution was smaller, was a few times, was a fraction of the wind effect. Okay, even though the wind effect was not at its peak, the density effect is like, if I remember correctly, 1/3 or 1/4 of the wind effect. And the wind effect, it can be even bigger. So because of that, the density effect is indeed not negligible. It's somewhere there, but not the major component.
Okay, thank you.
Yeah, you're welcome.
Otra pregunta. Can you comment? Have you ever investigated or do some inquiring about sand budgets with these currents and these transports that you have computed?
You mean suspended sediment?
Exactly, like the movement of sediment in these inlets.
That's a very good question. Let me see. The answer is no for the inlet. We had some graduate student did some work for the offshore simulation, but we did not really look at the sediment at the inlet yet. Even though we did measure the backscatter, everything, and in some cases we even had the water samples. That was a paper, uh, 3 papers. One paper published this year and a couple of papers published like 16, 15 years ago. That was the 24-hour survey. The idea was, like I said, there's a non-alias sampling, continuous sampling. We sampled 6 times of the water samples at 3 different levels at 3 stations across a 600-meter tidal channel, okay, tidal inlet. And we had 54 suspended sediment samples. We computed the organic, inorganic, suspended sediment transport concentrations and transport. We we were considering writing up another one just for that part, but the sediment transport was computed and presented in the paper that I can forward to you. I think it was 2011, a J.J. Ocean paper. We had some uh, results, but that was during the summer, a nice weather time. There was no cold front. Um, so in terms of cold front effect, no, we don't have that yet.
Okay, thank you. I think we have somebody else from the internet. Adelante,
¿Sí se escucha?
adelante, Angie.
Me gustaría que me tradujeras para preguntarle cómo identifica cuantitativamente los frentes fríos.
Okay, she's asking, how do you quantitatively identify cold fronts?
Okay, so the question is, how do I identify cold front, right?
Yeah.
Okay, a cold front that's a good question. The way we identify cold front, where one way kind of visual, kind of just kind of simple way is the visual way. We pull out the weather maps, and weather maps already show us where you have a cold front, right? That's one way to do it. But the second way is we can also verify with ground station observations. Like I mentioned, that the cold front has its characteristics of gradient, strong gradient. Any front is where you have a strong gradient, and that gradient includes at least 3 parameters. One is temperature, one is pressure, one is humidity. Okay, and the 4th parameter is wind, which is a little difficult to quantify it objectively, but you can still do it. you can see, especially for a strong cold front. For weak cold front, it does pose a challenge. Objectively pick it out, it's very difficult because especially in summertime, the cold front may reach the coastal region, then kind of disappear, or kind of move back, become a warm front, or stationary front, or just kind of weakened, and the wind just die out. That's possible. But what we do is we look at the pressure record, and you should have a sharp drop in pressure and then bounce back. That's a typical cold front. And if the cold front does pass, if it doesn't pass, like goes to the region and then retreat, then you don't have a passage, then you don't see that humidity change and temperature change. But usually a significant change will occur that will verify or kind of combine with the weather map, you can be sure there is a cold front, is that the temperature has a significant drop, and especially for humidity, okay, because the high pressure system carries air from the Arctic, from the northern states. So it's very dry from the land, and it's very easy to identify with not only temperature drop, but also most importantly, the humidity or dew point temperature is going to drop. I hope I answered your question.
Angie, ¿todo bien?
Yes, thank you.
All right. Well, I think we don't have any more questions. Nada. Un saludo. Thank you very much, Chunyan. Thank you for your presentation.
Thank you. Okay, have a good day.
Hopefully, we can have you coming here and to meet you in person.
Yeah, I would love to. Anytime. Well, actually, better. Well, we can pick some time. We can talk about that. Yes. I'll be glad to visit Sicel. It's on the other side of the Gulf of Mexico. It has a different climate, but I learned later that the cold front does reach your area, so that was kind of amazing. It will be nice if we compare the impact between our site and your site.
Cool. Well, thank you very much.
Thank you.
Bye-bye.
Bye.